Alright, so welcome back. We've got a new topic today on partial fraction decomposition. So our objectives won't make sense just yet, but we're going to determine partial fractions of a given rational function and then integrate those fractions. So to start off, what would I have to do to solve this?
Make the denominator same.
Okay, so I have to get a common denominator first. Okay, so if I wanted to solve this, I would get a common denominator, multiply everything out, then combine my like terms, and end up with 7x plus 16 over x squared minus x minus 6. Okay, what I want to do today is work backwards. I want to be able to take this fraction that we've already combined and break it apart into the partial fractions that we used to add together and equal this larger fraction. The reason why I want to work backwards is because right now if I tried to integrate this function on the left side, integrate 7x plus 16 over x squared minus x minus 6. I would start off by saying my u is my bottom part of this fraction. So this is x squared minus x minus 6. My u prime is 2x minus 1 dx, and then I would be stuck because that's not what I have on top. I could multiply through by 7 over 2 as a constant to get 7x minus 7 over 2, but that still wouldn't be what I have on top. So I'd still be stuck. So instead, we're going to try to work backwards from here, breaking this larger fraction apart into two smaller fractions that we'll be able to integrate much easier. Okay, I've got a couple people joining on Zoom. Can you guys hear me on Zoom? Okay. I can see your microphone's going, but I can't hear you. So let me see if I can fix that again. Okay, someone on Zoom, can you speak for me? Hello, thank you. Alright, I've got a couple people that are just joining. So really quickly, if I wanted to solve this addition, what I would do is get a common denominator, multiply, and combine like terms. What we're going to try to do today is work backwards. So go from here back to here. And the reason why we want to do it is because right now if I tried to integrate this larger fraction on the left side, I would be stuck. My u would be the bottom part, which is x squared minus x minus 6. My u prime would be 2x minus 1. And there's no constant that I can multiply in order to make this u prime what I have on top, the 7x plus 16. I can multiply by 7 over 2, but if I did, that negative 1 would become negative 7 over 2, which is not the 16 I need to substitute. So I'd be stuck. Okay, so here's what it looks like. I'm going to start out with our larger fraction, 3x plus 1 over x squared plus x. And the first thing I'm going to do is I'm going to factor. That'll tell us what the bottom parts of these original partial fractions were. So if I factor the bottom, I'll get x times x plus 1. Is there a way that I can zoom here? Yeah, there we go. Okay. Then for the next step, I'm going to assume that there's some constants we don't know that were here. So constant A and constant B that I need to solve for. If I wanted to add these fractions together, I would get a common denominator. So I'd have to multiply A times x and B times x plus 1. That leaves me with, since all of my bottom parts of these fractions are the same, if I multiplied the entire set so everything by what was on bottom, x times x plus 1, then my bottom parts of these fractions would cancel for every term. And that would leave me with a formula that we can start to use to solve for a and b. These are all of my numerators. So if I want to solve for a and b, first I can combine my like terms. So I'm going to put all of these x's together. So I have a plus bx plus b on the right side. Since all of my like terms have to equal each other, this a plus b must equal 3. And this b alone must equal 1. So that gives me a system of equations that we can solve. If b is 1, then a must be 2. So that means our original fraction, 3x plus 1 over x squared plus x, is equal to 2 over x plus 1 plus 1 over x. If I wanted to integrate this one on the right side, I could integrate directly using natural logs. I'll do that really quick. So I could say the integral of 3x plus 1 over x squared plus x is equal to the integral of 2 over x plus 1 plus 1 over x, since we've just proven that these two are equal. If I wanted to integrate 2 over x plus 1, then I could say u is equal to x plus 1, and u prime would be equal to 1. That's dx. So we could say, if I pull out the 2, this is 2 times the natural log of u, which is x plus 1, plus, if I integrate 1 over x, I'll get natural log of x, plus c. Any questions on what we did here? Okay. So there are a couple things to watch out for when we're doing this. The problem that we just solved is what we would call, what I'm going to call, a type 1 problem. I'm stealing this from Hull University, so they've got kind of a nice way of learning this for the first time. So type 1 is anything where you have linear factors. So that means your factors are x to the first power plus some sort of constant. So both of these factors are linear. And we can solve them normally, as we just did. If when you factor you end up with higher order factors, that's x squared, x cubed, x to the fourth, x to the fifth, any power that's not 1, then every higher order power has a possible term. So what that means is when I break this apart, this could be 3x plus 1 over x minus 1, x squared plus 1, could be equal to something over x minus 1 plus bx plus c, that's 1 degree less than x squared plus 1, over x squared plus 1. So I'll need another term on top for every power that is less than my highest power that I used for that factor. Okay, for type 3, we have a linear repeated factor. So in this case, x minus 1 is squared. We repeated that once. Times x plus 5. Well, if I expanded this, x minus 1 squared, I would get an x squared power. So it is possible for x minus 1 squared that I would have an x to the first power term in the numerator. So what I'm going to do is I'm going to write out my possible a and b terms for having an x to the first power in the numerator, but I'm also going to write another one that does not have that in the numerator. x minus 1 to the first power. I'm just reducing this by 1 every time. In the numerator, I'm reducing my powers by 1 every time as well. Plus, I could have some variable d over the x plus 5. That was not repeated. So anytime you have a repeated factor, you'll need to check for a solution that has 1 power less than that power. And then keep doing that for every power less than that power until you end up with 0. So for this x minus 1 squared, I also need to check for x minus 1 to the first power. If this was x minus 1 cubed originally, I would have to check for x minus 1 cubed on bottom, x minus 1 squared on bottom, and x minus 1 to the first power on bottom. And just keep reducing your power until you hit 0. Okay, any questions on type 1, 2, or 3? Nope. Okay, then the last one is an improper fraction. Improper fraction is whenever your numerator is larger than your denominator. I believe we saw some of these earlier, unless I'm mixing up my classes. So we'll need to use polynomial division or synthetic division to divide these out first, and then we can solve them normally. Okay, so I'll show you one of each type. So type 1, again, same idea as what we did in the previous slide. We have linear repeated factors. These are both x to the first power. So when I break these up, I'm just going to have constants in my numerators. We'll cross multiply, so this will be a times 2x plus 1 and b times x minus 1 to get my common denominator, and then set the numerators equal to each other to get our equation that we can use to solve for a and b. I notice this time I didn't actually multiply the a times 2x plus 1, I just left it out here. That way what I can do is I can take a look at this 2x plus 1 and try to figure out what number I could plug in for x that would make this equal to 0. That would mean I wouldn't have any a's left, and I would just have b's. So for instance, I'm going to solve this slightly different than what they did here. 2x plus 1 will equal 0 if x is negative 1/2. So if I use x is negative 1/2, my equation will become negative 3 over 2 plus 1 is equal to a times 0 plus negative 1 over 2 minus 1. Okay, what I've just done, times b, is eliminated all of my a's. So now all I have is b's and a constant, and we can use that to solve for b. Negative 3 over 2 plus 1 is negative 3 over 2 plus 2 over 2 is negative 1/2. Negative 1/2 minus 1 is negative 1/2 minus 2 over 2 is negative 3/2. So I'm going to multiply everything by 2 and then divide by negative 3 to get b is 1/3. Okay, you can solve these system of equations using any method you want, but we'll solve for a and b. Once we've got a and b, we'll plug them in here for our constants. So b was 1/3. So if I have 1/3 divided by 2x plus 1, that 3 is on the bottom of the fraction, so I can put that down here. 1/3 times 1 over 2x plus 1. Same thing for a, 4/3 times 1 over x minus 1. Okay, any questions on what we did here? Okay, a little bit more interesting. Type 2 is whenever we have a higher order power. So here I've got x squared plus 1. That's not a linear power. So what I'm going to do is my numerator will become a constant times every power less than whatever my highest power was in that nonlinear power. So my nonlinear factor was x squared something. So my numerator for that should have an x to the first power and an x to the 0 power, or bx plus c. Again, we cross multiply. And set the numerators equal to each other. So that was a times x squared plus 1. And bx plus c times x minus 1. Okay, then we can plug in any numbers you want in order to solve for a, b, c. So the first thing I'm going to do is I'm going to plug in x equals 1, because that'll make all of this equal to 0, and 0 times bx plus c would still be 0. So I would be left with just a's. If I do, when I plug in x equals 1, that gives me 1 plus 1 times a equals 3 plus 1. Therefore, 4 equals 2a, or a equals 2. Okay, then I can go back to the original problem. If I look at just my largest powers, so I look at just the x squareds, when I multiply, this will be a times x squared. And this will be bx times x is bx squared. Should equal 0x squared on the right side. So that means all of these coefficients should be equal to each other. If I factor out my x squareds, then my x squareds can cancel. A plus b must equal 0. So if a is 2, then 2 plus b equals 0, and therefore b is negative 2. Okay, then I can do the same thing for my constants. Which I guess I'll do up here. Oops, just move the zoom window. There we go. So for my constants, on the left side I have 1 for my constants. On the right side I'll have a times 1 is a. And then my bx, when I multiply through, will never be constant, so I don't have to worry about that term. So this will be bx times x, bx times negative 1, c times x, and then my only constant from this term over here is c times negative 1, or negative c. Okay, so using my constants, if we know that a is 2, then 2 minus c equals 1, and therefore c is 1. And that gives us a, b, and c. Any questions on how we solve for the constants? Okay. So now that I've got a, b, and c, we can put that back into our original problem, and we'll get our partial fractions. A is 2, b is negative 2, c is 1. Okay, type 3, we've got linear repeated fractions. Linear repeated factors, rather. This x minus 1 repeats itself twice. Anytime I've got a linear repeated factor, I'll need to check every power less than that. So I'm going to check x minus 1 to the second power and x minus 1 to the first power. So if I want to get a common denominator, I would have to multiply this term by x plus 5. A times x plus 5. I would have to multiply this term by both another x minus 1 and an x plus 5. Another x plus 5 and an x minus 1. I would have to multiply this term with c in the numerator times x minus 1 squared. That would give me a common denominator of x minus 1 squared times x plus 5. If I was going to write it all out, it would look like this. Okay, then we can set the numerators equal to each other. numerators equal to each other. And then solve for a, b, and c using any method you want. Okay, if I plug in x minus 1, that will get rid of this term with a b and this term with a c and leave it with just a equals something. So when x equals 1, this is 6 times a equals 36, so a is 6. If I plug in negative 5, then a's will cancel and b's will cancel. So if x is negative 5, this will be negative 6 squared c equals 36. Or 36 equals 36c. Therefore, c is 1. And if I look at the largest powers, so my x squareds, there are no x squareds on the left side, so that's 0, equals, I will not get an x squared for any a's. I will get an x squared for my first term here. So that'll be bx squared. And I will get an x squared for my first term here. It would be cx squared. So I could say, b plus c x squared equals 0. Therefore, b plus c equals 0. And if c is 1, b is negative 1. Okay, any questions on how we solved this one? So quiet. Thanks. Then the last one, improper fractions. So for improper fractions, we'll need to use some polynomial division to split this up before we start. So if we do, I'm going to multiply this out first. This is x cubed plus x minus 3x squared minus 3 on bottom. Or if I rewrite this, x cubed minus 3x squared plus x minus 3. I'm going to give myself some more space, I think. Did I freeze? There we go. Okay, so if I want to divide this, I'm dividing x to the fourth minus 2x cubed minus x squared minus 4x plus 4 by x cubed minus 3x squared plus x minus 3. So if I do, in order to get an x to the fourth power, I'd have to multiply this by x. That'll give me x to the fourth minus 3x cubed